Hi, these are the trigonometry lectures for educator.com, and today we're talking about computations of inverse trigonometric functions. So in the previous lecture we learned the definitions and we practiced a little bit with arcsine, arccosine, and arctangent. So you might want to review those a little bit before you go through this lecture. I'm assuming now that you know a little bit about the definitions of arcsine, arccosine, and arctangent, and we'll practice using them and working them out for some common values today. So the key thing to remember here is where these functions are defined and what kinds of values you're going to get from them. Arcsine, remember, you start out with a number between -1 and 1, and you always get an answer between -pi/2 and pi/2. It's very helpful if you remember the unit circle there. Arcsine always gives you an angle in the fourth and the first quadrant between -pi/2, 0, and pi/2. So you're looking for angles in that range that have a particular sign. Arccosine also between -1 and 1, and produces an answer between 0 and pi. Again, it's helpful to draw the unit circle and keep that in mind. There's 0, pi/2, and pi. So you're trying to find angles between 0 and pi that have a given cosine. Arctangent, you can find the arctangent of any number, and again, you're trying to find an angle between -pi/2 and 0 and pi/2 that has a given tangent. And I say exclusive here because you would never actually give an answer of -pi/2 or pi/2 for arctangent, because arctangent never actually hits those values. If you think of that coming from the other direction, we can't talk about the tangent of pi/2 or -pi/2 because those involve division by 0. So when we're talking about arctangent, we'll never get -pi/2 or pi/2 as an answer. So let's practice finding some common values. So here are some common values that we should be able to figure out arcsines of. And let me start by drawing my unit circle. So there's -pi/2 and 0 and pi/2. Remember, our answer is always going to be in that range. And so let me just graph those common values and see what angles they correspond to. So I'll make a little chart here, x and arcsine x. So we got -1, -√3/2, -√2/2, -1/2, 0, 1/2, √2/2, √3/2, and 1. So remember, sine is the y-coordinate, so I'm looking for an angle that has a y-coordinate of -1 to start with. So I want to find an angle that has y-coordinate down there at -1, and that's clearly -pi/2. So that's the answer. -√3/2, that's an angle down there. So the angle that has sine of -√3/2 must be -pi/3. -√2/2, that's the one right there, so that's -pi/4. -1/2, the y-coordinate -1/2 is right there, that's -pi/3. And arcsine of 0, what angle has sine 0? Well, it's 0. What angle has sine of 1/2? Well, what angle has vertical y-coordinate 1/2? That's pi/3. √2/2, that's our 45-degree angle, also known as pi/4. And root 3 over 3, that's our 60-degree angle, also known as pi over 3. And finally, we know that the sine of pi over 2 is 1, so the arc sine of 1 is pi over 2. So in each case, it's a matter of looking at the value and thinking, okay, if that's my y-coordinate, where am I on the unit circle? What angle between negative pi over 2 and pi over 2 has sine equal to that value? And of course, if you know your values of sine very well, then it's not too hard to figure out the arc sine function. So you really don't need to memorize these. You just need to know your common values for sine x very well, and to know when they're positive or negative, and then you can figure out the values for arc sine x. In our second problem here, we're asked to find which of the arc sine, arc cosine, and arc tangent functions are odd or even or neither. And it's really, the key to thinking about this one is probably to think about the graphs and not so much to think about the original definition of odd or even. So let me write down the important properties to remember here. An odd function has rotational symmetry around the origin. The way I remember that is that 3 is an odd number, and x cubed, y equals x cubed, has rotational symmetry around the origin. Even functions have mirror symmetry across the y-axis. And the way I remember that is that 2 is an even number, and the graph of y equals x squared has mirror symmetry across the y-axis. So that's how I remember the pictures for odd and even functions. And now let me draw the graphs of arc sine and arc cosine and arc tangent, and we'll just test them out. So arc sine, remember you take a piece of the sine graph. There's sine x, or sine theta. Arc sine, I'll draw this one in blue. It's the reflection of that graph in the y equals x line. So that's arc sine x in blue. And now if you check that out, that has rotational symmetry around the origin. So arc sine x is odd. Let's take a look at cosine and arc cosine. Cosine, remember, you got to snip off a piece of the cosine graph that will make arc cosine into a function. So there's cosine theta. And now in blue, I'll graph arc cosine. So there's arc cosine x in blue. Now that graph is neither mirror symmetric across the y-axis, nor is it rotationally symmetric around the origin. So it is not odd or even. Which is a little bit surprising because even though, if you remember, cosine theta is even. So it turns out that arc cosine of x is not odd or even though cosine theta was an even function. And finally, arc tangent. let me start out by drawing the tangent graph, or at least the piece of it that we're going to snip off. Kind of looks like the graph of y equals x cubed, but it's not the same as the graph of y equals x cubed. One big difference is that tangent of x has asymptotes at pi over 2 and negative pi over 2, and of course y equals x cubed has no asymptotes at all. So what I've just graphed here is tan theta, and then in blue I'll graph arctan theta. So I'm flipping it across the line y equals x. It also has asymptotes, and these are horizontal asymptotes. So that blue graph is arctan x. And if you look at that, that is rotationally symmetric around the origin. So that's also an odd function. So this problem is really kind of testing whether you know what the graphs of arcsine, arccosine, and arctangent look like. And if you don't remember those, then you go back to sine, cosine, and tangent, and you snip off the important pieces of those graphs, and you flip them around the line y equals x to get the graphs of arcsine, arccosine, and arctangent. Those are the graphs that I have in blue here, arcsine, arccosine, and arctangent. And then the other thing that this problem is really testing is whether you remember the graphical characterizations of odd and even functions. So if you know that odd functions have rotational symmetry around the origin, even functions have mirror symmetry across the y-axis, it's easy to check these graphs to just look at them and see whether they have the right kind of symmetry. And of course, what you find out is that arcsine x has rotational symmetry, arccosine x doesn't have either one, and arctangent x also has rotational symmetry. So for our third example here, we're trying to find arccosine of the following list of common values. And again, it's useful to start with a unit circle here. And once you start with a unit circle, remember that with arccosine, you're looking for values between 0 and pi. Arccosine is always between 0 and pi. So we're looking for angles between 0 and pi that have cosines equal to this list of values. So I'll make a little chart here. Negative 1, negative root 3 over 2, negative root 2 over 2, negative 1/2, 0, 1/2, root 2 over 2, root 3 over 2, and 1. So remember, cosine is the x value. So I'm going to draw each one of these values as an x value, as an x coordinate, and then I'll see what angle has that particular cosine. So negative 1, the x coordinate of negative 1 is over here. Well, clearly, that's pi. That's the angle pi. Negative root 3 over 2, I draw that as the x coordinate. And that angle is 5 pi over 6. Negative root 2 over 2, I'll draw that as the x coordinate. I know that's in a 45-degree angle, and so that's 3 pi over 4. So that's the arccosine of negative root 2 over 2. Negative 1/2, if we draw that as the x coordinate, that's a 30, 60, 90 triangle. That's 2 pi over 3. What angle has cosine 0? That means what angle has x coordinate 0? That's pi over 2. What angle has cosine 1/2? Again, a 30, 60, 90 triangle, so that must be pi over 3. Root 2 over 2, that's a 45-degree angle, so that's pi over 4. Root 3 over 2, that's a 30, 60, 90 angle again, so that's pi over 6. And finally, what angle has x-coordinate 1? Well, that's just 0. So the trick here is remembering your common values of cosine on the unit circle. I know all the common values of cosine on the unit circle very well because I remember my 30, 60, 90 triangles, and I remember my 45, 45, 90 triangles. And I know which ones are positive and which ones are negative. And then finally, I remember that arc cosine is always between 0 and pi. So I'm looking for angles between 0 and pi that have these cosines, and so these are the angles that have the right cosines and are in the right range. So we'll try some more examples of these later.